Thanks for attending another one of my video lectures. Whether you're a student of engineering or applied mathematics, or a professional, you will obtain a deeper understanding of the following topics from this lecture: network flows, electrical circuits, and loop currents. This video gives further details on loop currents, which I mentioned in another video on trusses, electrical circuits, and Kirchhoff's laws. I will give a link in the description. But this video can be viewed independently of that other video, either before or after. My name is Charles DeMatos. I am a retired lecturer from the University of the West Indies, St. Augustine, Trinidad. The university supports my video creation by providing me with a workspace and other assistance. So I greatly value the support of the university, and I hope I can present a video of the quality required of their standards. Thank you. Example 1. This diagram represents a network. A network consists of nodes, which are depicted by these black dots, and branches. The branches are the lines that connect two nodes. So the straight lines here represent branches. In graph theory, instead of nodes and branches, we say vertices and edges. But for now, we will use the terminology of nodes and branches. You can think of this network as a network of pipelines, for example, carrying some fluid like water, oil, natural gas. Or you can also think of it as an electrical network where the branches are conductors, for example, wires or electrical cables, things of that kind. Now, to the network, we apply inputs and outputs. The arrows into the network represent inputs. The arrows away from the network represent outputs or flows out of the network. And each arrow has a number attached. This is the amount of flow into and out of the network. Now we can check here that this is a balanced set of flows. In other words, the total input equal to the total output. Let's check the inputs first. You have 1 and 3. That's 4 and 5, 9, 9 and 7, 16. And the outputs are 2, 4, 4, 6, which also add up to 16. So here you have equal inputs and outputs. The total input equals the total output. So this is what is called a balanced flow into the network. Or you can think of it as a balanced flow out of the network. If you think of the flow inputs as positive and the outputs as negative, the total will be 0. Now what we assume is that at each node the flows into the node equal the flows out of the node. In other words, you have equilibrium at each node. And what I will show you now is that the flows in each branch of the network can be found, and you have a unique answer. There's only one possible solution. I'm assuming, of course, the equilibrium at each node. So let's start with this branch. I'm assuming that the flow out here would equal the flow in. So along this branch, I'm assuming equal the same flow all along the branch here. The flow along this branch is 2, so equal input to this node as the output. Now let's consider this node here. You have an output of 2 units, so you must have an input of 2 units. So the flow along this branch will be 2 units, and therefore the flow away from this node will be 2. Now it's not possible to calculate the flows in all 3 of these branches at this time, because you have 3 unknowns here. So what we do, we keep looking for nodes where you have just one unknown flow. So for example, at this node you have just one unknown. You have an input of 5 and the output must be 5 also to balance that. As yet we do not have a way of computing these 2 flows in these 2 branches. So let's go to a node where there's only one unknown. Let's go to this node. You have an input of 7, you must have an output of 7. So the flow along this branch is 7. Now along this branch you do not know the flow, so but at this node there's just one unknown. This is the only unknown branch for this node. So you have an input of 7, an output of 4, so you must have an output of 3 also to give you 0 net flow into this node. So you must have a flow of 3 along this branch. Here we are in a position to find the flow in this branch because we know all of the other flows along the other edges. So this is the only unknown, and we can deduce that this is 6 units along this branch, because you have 5 in and 3 in. That's a total of 8 into the node. So if you have 2 here, you must have 6, because the 2 and the 6 add up to 8 to balance the inputs. So you have 6 units along this branch. Now let's go to another node where you just know you just have one unknown. At this node you have 4 out of the network, and you must have 4 into this node also to balance that flow. Let's go to this node. You have 1 unit into the node, you must have 1 unit out of the node. So 1 unit flows along this branch. At this branch you have 1 unit flowing in, you must have 1 unit flowing out. Now there's only 1 unknown at this node now, so it's possible to calculate the flow along this branch, but let's do it in a different order here. So at this node you also have 1 unknown, so you have 3 in, you must have 3 flowing along this branch. At this node you have 6 flowing out. You have 3 flowing in, so you must have another 3 flowing in. The 3 and the 3 will make up the 6. Now we can use this node to verify our calculations. You have 6 flowing in and 1 flowing in, that's 7 in all. You have 4 flowing out, 3 flowing out, also equal to 7. So this shows equilibrium is established at this node. So here we have solved all of the flows in the branches of the network just using equilibrium conditions alone. Okay, we were able to find all of the flows, and the solutions here are unique. There's no other possible flow that will result in equilibrium. You can think of these numbers here as rates of flow. In other words, it can be the volume per second, for example, number of cubic feet or number of liters per second, or some other, or it could be mass flow, for example, number of kilograms per second or number of kilograms per hour, and so on. So these can be considered as rates of flow. In the previous analysis, the equilibrium conditions assume incompressibility of the fluid or steady state conditions. An incompressible fluid is one like water, where small changes of pressure do not create any significant changes in volume. It's very difficult to compress it into a smaller volume. So we can assume a steady rate of flow along a given length of pipeline. For example, if water is flowing along the pipeline, the rate of flow out of this node is equal to the rate of flow into this node, because no water is accumulating along the pipeline. So whatever rate of flow out is out of this node, that same rate occurs into this other node. So the flow all along the length of the pipeline remains the same. For a compressible fluid, it's possible that the fluid will accumulate within the pipeline. For example, natural gas is compressible, so it's possible that the fluid will accumulate in the pipeline, or it will expand within the pipeline. However, under steady state conditions, even with a compressible fluid, you can assume steady mass flow rate. Even though compression occurs, the mass leaving this node per second equals the mass entering this node per second. This is under steady state conditions. In example 1, the type of network was what is called a tree. A tree is a connected graph with no cycles. You'll see on the previous slide, on the previous example, there were no cycles in the network. We will show what a cycle is down below here. Let's look at these 4 nodes. 1, 2, 3, 4. You can go from one to the next one, to the next one, and back to the starting node, just following the pipelines. So it's possible for fluid to circulate and come back to the initial node. In a tree, there are no cycles. We saw this on the previous slide. A tree is also connected. Connected means that fluid can travel from any node to any other node along the pipelines. We'll state our main result here. If a balanced set of flows is applied to a network that has a tree structure, then the flow in each branch of the network can be uniquely determined. This is what we did on the previous slide, example 1. We obtained the flow in each branch of the network. Okay, we had a balanced flow, set of flows, and it was a tree structure, so we were able to find the flow in each branch uniquely. Now let's look at example 2. This is similar to example 1. We have a different structure for the network here, but let's look at the flows. You have 3, 7 and 5. That's 15 units entering the network. Sorry, you have also 1. That's 16 units entering the network. Let's look at the flows leaving the network. You have 6 and 4 and 4 and 2. That's 16 also leaving the network. So you have 16 entering and 16 leaving. So it's a balanced set of flows. And the network is in the form of a tree. It's connected because you can go from any vertex, any node, to any other node. If you hear me saying vertex instead of node, it's due to habit, because I used to teach courses in graph theory at the UWI. And there are no cycles in this network. There are no cycles, so it's a tree structure. Once it's a tree and you have a balanced set of flows in and out of the network, you can use the method that we used in example 1 to find the flows in each branch. Let's do that. So if we start with this vertex, 3 is entering the network, so 3 units must flow along this branch. Let's look at this node here. 1 is entering the node, so 1 unit must flow along this branch. Look at this node, 5 units entering, so 5 units must be flowing along this branch. Let's look at this node. For equilibrium, if 5 is entering, you must have a total of 5 leaving. So if 3 is exiting here, sorry, if 2 is exiting, the remaining 3 must flow along this branch. And let's look at this node also. You have 3 entering and 1 entering from this branch, so a total of 4 will be flowing along this branch. Now here you have 3 units entering, 4 entering from this branch, so you must have 7 units flowing along this branch. And then at this node, 7 units entering, so 7 units must be flowing along this branch. Now let's go on to another node. Yes, we go up here, so you have 7 entering here, so you have 7 units flowing along this branch. And if 7 is flowing along this branch and 6 is exiting here, you must have 1 unit flowing along this branch. Now where will we go now? Let's look at this node. 4 units entering, so you must have 4 units flowing along this branch. And then we will look at this node. 4 units leaving here and another 4 units leaving along this branch, so you must have 8 units flowing along this branch. Now this last vertex, we can just verify that you have equilibrium. So you have 7 and 1 entering, 8 leaving, so it's in equilibrium here. And this is a solution. Again, we've solved the network using very simple arithmetic. This can be done by students in elementary school. We just find the flow, the unknown flow at each node that will provide equilibrium. Now let's try to understand why this works, why what we have done in the first 2 examples, why this method we've used in the first 2 examples works. Why does this work? It's because of the tree structure. In a tree, you have these nodes which are called end nodes. In other words, you have one edge incident with the node here. See here, at the moment, you have 2 edges incident, or 2 branches incident with the node here. Yeah, I'm going to say edges instead of branches, but that's just habit because I used to teach graph theory at the UWI. So here you have 4 branches incident with this node. Now, in our method, what we did was we looked at nodes where you just had 1 unknown. So initially, if the network is like this, at this node you would have 1 unknown, which is the flow in this branch. So if you have inputs and outputs at that node, you just have 1 unknown to solve for, so you can obtain the flow in this branch. Okay, so this is what we call pruning a tree. Pruning a tree means removing an end node. Right, so I should really remove the node also as well as the branch, but I just don't have the technical ability to do that as yet. So we remove the end node here. Just imagine that being removed, and we get a remaining network which is also a tree. And we look for another end node, and that gives us a node where we can look at the equilibrium conditions and find the flow in the branch next to it. So again, so this was an end node. It had just 1 edge and 1 branch incident with it. We can find the flow in that branch. We can remove it, which is called pruning the tree, and we obtain a smaller network. The smaller network is still connected, and it's a tree also. So we go ahead, we look at another end node, and we can find the flow in that, because we just have whatever inputs and outputs here. We just have 1 output, so we can find that flow in this branch, and then we remove the node and the branch, obtain a smaller tree, and keep going. So again, we can find if once we know the inputs and outputs here, we can find the flow in that branch. We get a smaller network, and it keeps shrinking like that. Okay, we just had one unknown here. We can find the flow in that and keep going. And here we just had one unknown. Here we can look at any of these three nodes, find the flow in the unknown branch with the unknown flow. Okay, we can find the flow here, and so on. We can keep going like that. So that's why this method works when you have a tree, because there are always end nodes, which would give you exactly one unknown that you can solve for, and you can keep going and find all of the flows in the network. So this method we've done in examples 1 and 2 works because of the tree structure of the network. Let's go to example 3. You can verify that this network has a tree form. You can verify it's connected, there are no cycles. You can also verify that it's a balanced set of flows. You can verify that the flows entering add up to the total flow leaving the network. But you can also see it's balanced by observing this fact. You have 2 entering here and 2 leaving, 3 entering, 3 leaving, 4 entering, 4 leaving, 5 entering, 5 leaving. And those are all the flows. So for any flow entering, you have an equal and opposite flow leaving. So you must have a balanced flows in a situation like this. In a case like this, we can use what I call the method of paths. So let's see how this works. Let's look at the flow here, 2. Let's start at this vertex. Now you have 2 flowing into the network here and 2 flowing out of the network here. So what we will do is use a path from this vertex or this node to this node. Okay, so we'll take flow of 2 down this branch, another flow of 2 down this branch, another flow of 2 down this branch, 2 up that branch, and 2 across here. So that takes care of the flow of 2 in here and out here. You can just imagine that flow going along this path, in here and 2 out here. Now let's look at the flow of 3 here. You want 3 entering here and 3 leaving. What we will do is find a path from this node to this node. And so 3 entering here must flow along here, 3, and then 3 along this branch, and then 3 down this branch. It will add to the 2 here, and then 3 along this branch. It will also add to the 2, and then 3 along this branch, and then out. Alright, so because of the paired flows in and out and the paths joining those 2, you can create this kind of situation. Now let's look at the flow of 4 entering here. We have another 4 leaving here. So we follow a path from this node to this node. So from this node you go down here 4, and then you go across here. I'm using the arrow to indicate the direction. So 4 goes across here, and then 4 flows down here again. Then you have another 4 moving across, so that will add to the 2 here. And then the flow 4 goes out here. Now we have to look at the 5 now. 5 enters here and 5 leaves here. So again, we will think of this 5 as flowing along a path joining these 2 nodes. So we start here. So this flow of 5 goes along here, and this flow of 5 goes along here, but it's going opposite to the arrow, so we have to subtract 5 from this, from the total here. And then the 5 goes up here, so it goes against the arrow, so this gives you a minus sign here, minus 5. And then the 5 has to go across here, so again this goes opposite to the arrow, so we subtract 5 here, and then the 5 goes out. And that takes care of all of our inputs and outputs: 2 to 2, 3 to 3, 4 to 4, 5 to 5. Now what we do now is to simplify these numbers. The 2 and the 3 add up to 5, and this gives us a total of 5 along here. And then when you add these numbers, subtract 5, you get a total of 4. So you have 4 along this branch here, and then you'll have 6 minus 5, you'll have 1 unit going across here. Now here you'll have 4 minus 5, this gives you -1. A negative sign means that the direction is reversed, so we will reverse the direction of the arrow here, and we will summarize that. We'll summarize that. Okay, so what I'm saying here is that the 2 and 3 gives you 5 here. I'll remove those numbers. The 4 and minus 5 gives you -1, so I'll simplify that. These numbers add up to -4, and coming here, these numbers add up to 1, so I'll remove that, and then I will change the direction here because of the minus sign, so it becomes 1 in this direction. You can verify going node by node that you do have equilibrium conditions. So in this method of paths, you will end up with equilibrium at each vertex, because along a path, whenever you enter with a certain value, you leave with an equal value in the opposite direction, so you will maintain equilibrium at each vertex when you add up those paths. This is the same example as in example 1. In example 1, we use the method of going vertex by vertex and solving for the unknown, okay, for a single unknown. But what I'll do is I will modify the method of paths to solve this network. Even though the paths are not, even though the flows are not matched, okay, I have a 1 entering here, but I don't have a 1 leaving, I can still modify the method of paths to solve this network. Let's start off. So here I will look at these flows, the 5 and the 7. This gives me 12. I want to match that with an equal. I have 12 entering. I want to match that with an equal leaving. Okay, I have this 4 and this 6 and this 2 add up to 12. So I'll balance the 5 and the 7 with this 6 and this 4 and this 2. So I have 5 going across here, 7 and 7. Alright, 7 and 7. Yeah, so I'm ignoring this 4 for now. I'm just looking at the 7 and 7 here. 7 here and 7 here. I'm not diverting part of the 7 down here. I'm just following through here. And now this 5 and 7 will make the 12. So I have to distribute this to the 2, the 4 here, and the 6. So I will send 2 up here and 10 across here. So the 5 and the 7 will be diverted into 10 and 2 here. Now this 10 I'll divert into 4 and 6. So that gives me 4 upward and 6 downwards. So I've taken care of these 2 inputs and the 3 outputs here. 2, 4, and 6. Now let's look at the remaining inputs. I have a 1 in here, a 3 in here, and a 4 out. What I'll do is try to get these 2 to merge into this 4. So I'll have 1 coming down here and across here, and 3 going across here, and then upward here. So it's a -3 because it's against the arrow. So the 1 and the 3 will add up here, and I will send that across this branch so it becomes -4, and then down this branch so it becomes a -4, and finally out. So this 1 and the 3 merge into 4 and flow out here. And then I will simplify the numbers. Here the numbers have been simplified. You can verify that at each node there is equilibrium. You can do this for each node, and you can see that this method works, this modified method of paths. Now again, why does this work, this method of paths and the modified method of paths? Well, it works because of the uniqueness of paths in a tree. In a tree structure, there is a unique path connecting any 2 nodes. In other words, exactly one path. And this is why, if you go back over those examples, you see that from when you had an X in and an X out, there was exactly one path, one way to get from the input to the output. So because of the uniqueness of paths, the solution here is unique. In other words, you can work it out, you can do this in any order, and you come up with the same result each time. Now, so far we have been only working with tree structures, tree networks. But what if cycles are present? What if it's not a tree and cycles are present? Well, let's look at this example. You have here a network which has a cycle, so it's not a tree. And if you have an input of 3 here and an output of 3, there are different paths you can go from the input to the output. You can go along this branch and this branch, or you can go along this branch and this branch. So there's no unique way of solving the problem here. Right, you can go along this path 3 and 3, or you can go along the other direction. So this is one possible solution to the network problem. And of course it's not unique because you can go along the other two branches also. You can see also that the method of equilibrium at each vertex doesn't work either, because at this vertex, when you have the 3 here, you have two unknowns here, so you will not be able to solve uniquely for the 2 unknowns. Similarly for all of these. And even worse than that, you can see that if I use this direction for the other branches, if I add x to the flows along this cycle, I can add any value of x that I like, positive or negative, and you still have equilibrium at each node here. You still have equilibrium at each node. Just verify this. The x could be anything. You can put x equal to 5, 10, anything, and it will give you a solution. It will give you something that solves the equilibrium conditions. So there's no unique solution when you have cycles in your network. Now let's go to example 5. Here we have a case of a network with exactly one cycle. So we have balanced a set of inputs, 3 in, 3 out, 2 in, 2 in, 2 out, 5 in, 5 out. Of course, these are paired inputs and outputs. But because of the cycle, we know that there's no unique solution to the problem. But what if we could measure the flow along one branch of the cycle? Suppose we have some meter that can measure the flow along this branch, and we measure the flow along this branch to be 4. In a case like that, we can solve uniquely for all the flows in the branches. So what we do for this branch that we measured, we know it has a flow of 4. What we do, we replace this by a 4 entering that vertex and a 4 leaving that vertex. So we know the flow from this vertex, from this node to this node, is 4. We simply replace that by an input of 4 here and an output of 4 here. And then, since we've removed this branch, we now have a tree structure because we've gotten rid of the cycle. And with a tree structure, we can do the method of paths as we did before and find the flows in all of the branches. So let's do that. So for this pair 4 and 4, we take a path from this vertex around to this vertex. So we have 4 here, 4 down, 4 down, 4 across, and 4 up to this vertex. And we do the same thing for each pair. So for the 2s, for example, alright, for the 3s, we go along here, 3, we are trying to get to this vertex, so we keep going, plus 3 there, plus 3, plus 3, and 3 across here and out. And for the 2, we are trying to go from this vertex to this vertex, so we come down here, 2, and then plus 2 here, plus 2, and plus 2. And for the 5, we have 5 in here, and we are trying to get to this vertex. Exactly one path again. plus 5, minus 5 because we are going against the arrow, and then minus 5 because we are going against the arrow, and 5 across here. Okay, so once we've reduced to a tree, everything is simple. A child can do this. Anyone who can add and subtract can do this kind of thing. So next we will simplify the numbers. So we simply simplify the numbers, take into account the plus or minus sign. If you have a negative, we can reverse the arrow, and we get this solution. So we have our 4 along this branch. You can verify that at every vertex there is equilibrium. It flows in equal to the flows out. So we obtain our solution. Now we will go to the topic of electrical circuits. In an electrical circuit, generally there are no external inputs or outputs. The flows are only possible because of the cycles in the network. So it's only because of cycles that you have flows in the network. There's no you don't consider any possible external inputs or outputs. How can the flows in each branch be measured? Well, we can put meters, as we did in the previous slides. We can put meters to measure the flow along a circuit. Okay, so along the circuits, if we can measure one of the branches, it's possible to find the flows in other branches of the network. So in the previous example, we had one cycle in the graph. Here we have lots of cycles. But what if we can measure the flows in these branches? Okay, we put a meter along this branch. We can measure the flow here, W. We can measure the flow along this branch. Suppose we put a meter and measure this to be X. And the flow along that branch, suppose we put a meter here and measure the flow to be Y. And along this branch, suppose we measure the flow to be Z here. Can we find the flows in all the other branches? Can we find a unique solution for the flows in the other branches? Well, let's try it and see. Okay, so we measure these branches W, X, Y, Z. Again, if we follow what we did before, when we had loops, instead of the flow along that branch, we replace it by an input here of W and output here of W. And instead of the Y going across here, instead of the X going in that direction, we replace this by an X output here and an X input here. And instead of the Y flowing across here, we replace that by a Y leaving here and a flow of Y entering here. And instead of the Z, a flow of Z out here and then the Z in. Now if we do this kind of arrangement, can we find the flows in the other members? Well, the answer is no, because the remaining branches form a cycle. Although we have a balanced set of inputs here, okay, it's balanced because whenever we have a W in, we have a W out, X in, we have X out, etc. It's balanced. But the unknown branches have a cycle, so we cannot uniquely solve for the flows in the other branches. Okay, we cannot determine all the currents uniquely. On the previous slide, we measured 4 flows. We measured W, X, Y, and we measured Z along this branch. And in that case, we saw that we could not obtain values for the flows in the remaining branches. Part of the reason for that is because a measurement of Z along this branch is a bit redundant. Once I know values of W, X, and Y, for equilibrium to occur, the value of Z must be in this direction, and the sum of W x plus y, W plus x plus y, in this direction. So it's not necessary, once I have W, X, and Y, to take a measurement on this branch. So let's do something else instead. Let's measure the Z along this branch. Let's see what happens in that case. We do the usual procedure. We replace the flow along that branch with a balanced flow W in here and W out of the network here. Instead of a flow of Y along that branch, we remove the branch, instead of a flow of X here, we remove the branch and replace it by an input of X here and an output of X here. Instead of the flow Y along this branch, remove the branch, replace it by a flow of Y in here and Y out here, and instead of Z along that branch, remove the branch, replace it by Z in and Z out at those nodes. Now you can see here the remaining network, which are the unknown branches, is a tree. It's a tree structure. It's just a single path, but it's a tree because it has no cycles. And again, once we have a tree structure and a balanced set of inputs and outputs, in this case it's paired, we are able to find the flows in all of the branches of the network. So we can find all of the flows in the remaining branches uniquely in this case. So let's see how we can express the flows in the unknown branches in terms of W, X, Y, and Z. As we did before when we had the balanced flows, for an input of W here and output of W here, we can think of this flow W as going along this path from this vertex to this vertex. So start here, we have W flowing along these branches and ending here. Now for the flow of X in and out of these vertices, we can think of the X flowing in here and going around and flowing out here. So the X's are added because they go in the same direction as the arrows. So it's added along these branches. And for the Y's, think of an Y flowing from this vertex, from this node to this node to this node. We'll have to go all the way around. So again, it's added here, plus Y, plus Y, plus Y. And we are following the method of paths here. For the Z enters here and goes around this path and ends here. So it's plus Z, plus Z, plus Z, plus Z, plus Z, and ends here. So once we have measurements of W, X, Y, Z, we can express the flows in all of the other branches in terms of W, X, Y, Z by means of these formulae. Again, as we said before, we can take measurements on those branches whose removal will result in a tree. So we take measurements not in an arbitrary way, but on those branches whose removal will result in a tree structure. So once we have a tree structure remaining, we can apply the method of paths and express the flows in all of those unknown branches in terms of our measurements. Now, when the method of paths is applied, cycles are formed. If you look at the W here, we replace the flow of W across here by an input of W and an outflow of W here. But just remember that this is only for computational purposes. There's an actual branch here, so you have an actual flow of W going along this cycle. So it goes along a complete cycle here and goes along here again. Similarly for X, there's an actual branch here, so in the actual network you can think of a flow of X going along a cycle here, and you can think of a flow of Y going along a cycle here in this direction. So the actual flows in the network can be expressed as the sum of these cycles, the sum of the flows along these cycles. Now, any flow of current that satisfies Kirchhoff's current law will be associated with a unique set of values of W, X, Y, Z. Kirchhoff's current law is the same as our equilibrium conditions in the case of electrical currents. In Kirchhoff's current law, the currents flowing into a node equals the current flowing out. Or you can think of it as the algebraic sum of the flows into the node is equal to 0, which is the same as our equilibrium conditions. So what I'm saying is that for any arbitrary flow of current satisfying Kirchhoff's laws, once we take these measurements, W, X, Y, Z, that tells us everything about, that represents uniquely the flow in the current. So any flow of current that satisfies Kirchhoff's law is associated with a unique set of values of W, X, Y, Z. These are the measurements that we can take to represent the flow in all of the members, in all of the branches of the network. In electrical circuit theory, instead of choosing branches to be removed to form a spanning tree, loops, which are cycles, are selected. These loops may or may not be cycles obtained using the spanning tree approach. Usually the circuit is drawn as a planar graph. So in the method of loop currents, the circuit is usually drawn as a planar graph. This is an example of a planar graph. I'll say more about planar graphs later, but basically you do not have the branches crossing each other. They only meet at the vertices. So think of this as a map, and this is one region, one state, or one county. This is another state or province. This is another state or province. Think of it as a map, and each region corresponds to a loop. So in this region you have this loop S. Here you have this loop. In this region you have this loop T. Okay. Along this cycle in the circuit you have this loop U, and along the cycle you have a loop V. So you can think of these as currents circulating, just as we had in the previous slide. You had circulation of currents represented by variables W, X, Y, Z. Think of these loop currents in a similar way to the currents we had circulating in the previous slide. And then you can express the currents in each of the members by the loop currents. So what we do, we introduce an arbitrary orientation of the branches. Orientation means we give a direction to the branches indicated by the arrows as shown. This could be arbitrary, okay? I did not have to do it this way. I could have easily reversed any of these arrows. And then let's look at the first loop here with the S. So think of the S as a current circulating around this loop in this clockwise direction. So you'll have S flowing here. I have S flowing up here, S flowing here, T flowing here, T flowing here. Okay, so I go here, T and T, and on these branches you have U flowing here and U flowing here. Okay, U flowing here, and then on these branches you have V flowing here and V flowing here. Okay, all right. Well, these are the obvious currents. Okay, the only current, the only loop that contributes to this branch is S, and similarly S, and then U here, V, V, T, T. Okay, now let's look at the other branches. For this branch here, it's in this direction, it's in the same direction as S, so the loop current contributes plus S to this. But here, if you follow the direction of U, it goes in the reverse direction, so the loop current U contributes minus U to this branch. Similarly here, the arrow follows the direction of S, so it's plus S here, and it's in the opposite direction of the loop current T, so you have minus T contributed here. And then on this branch is plus T because it goes in the same clockwise direction as the T, but it's in the reverse direction as the V, so it's minus V here. And then for this branch it's plus U and then minus V going in the opposite direction. So here, using the loop currents ST, U, V, we can express the currents in all of the branches in terms of these four variables. So to express any current in this network, in this circuit, we just need four numbers, ST, U, V, and we can express all of the currents in this network. Kirchhoff's laws will be followed. You can just check algebraically that at each node here, the sum of the inputs equal to the sum of the outputs algebraically. So this represents all of the possible currents in the network, in the circuit, satisfying Kirchhoff's current law. As I mentioned, any flow of current satisfying Kirchhoff's current law corresponds to a unique set of loop currents. Equivalence between the representation as cycles from a spanning tree and loops can be shown. We'll show that later on. This equivalence is most easily shown when the electrical circuit is drawn as a planar graph or map. In a planar graph, the edges or the branches do not cross except at the nodes. Let's suppose we have a circuit with 4 nodes. And here you have these 6 branches. You have all possible pairs joined by a branch. Now, the circuit on the left is not drawn as a planar graph because here you have edges crossing. Here you have edges or branches crossing. And this is not what is called a planar graph. In a planar graph, you draw the circuit without any edges crossing. So this circuit is actually the same as this circuit, because notice any 2 nodes are joined by a branch. This is the same thing here. You have 4 nodes and any pair of them are joined by a branch. So basically this circuit and this circuit are the same but just drawn differently. And here this is in the form of a planar graph because of the absence of edges crossing, unlike this. So this is the form we would draw the circuit if we are looking at loop currents. So in each region here, you'll have a loop current. In this region here, in this triangle, you'll have a loop current. In this triangle, you'll have a loop current. So you would draw the circuit in this form if you are using the method of loop currents, rather than draw it in this way. Although it can be done in this fashion also, but it's better to have it as a planar graph. Previously, I showed that any set of currents satisfying Kirchhoff's laws can be represented by currents in cycles formed from a spanning tree. And then I claimed that any set of currents that satisfy Kirchhoff's laws can be represented by loop currents. Now I want to show why that second statement is true. I want to show that any flow of currents that can be expressed in terms of the cycles from a spanning tree can also be expressed in terms of loop currents. So at the top figure is our electrical circuit, and it's drawn as a planar graph, and it's easy to identify the loop currents. Just look at the regions here. There are 6 regions, and you can attach a loop current to each one of those. So the first region here, you associate a loop current I1, and then to this region I2, I3, I4, I5, I6. So there are 6 loop currents here. In the diagram below, you have a spanning tree obtained from this circuit. Okay, it's a spanning tree because it's connected and there are no cycles. Now, for each edge that we removed to form this spanning tree, we can obtain a cycle from the, if we add back that edge. So for example, this edge that we removed to form this spanning tree, this, if we associate a current along that edge, we will obtain a cycle. So suppose that cycle is C1. Using the direction of the arrow here indicating the orientation, you can see that this cycle formed from the spanning tree is the same as the loop current I1. So I'm writing here C1 equal to I1, and let's look at another cycle formed from the spanning tree. If I use the edge here that was removed with this orientation, I obtain a cycle C2. Now C2, of course, it doesn't include that edge. It just has the edges. The rest of the edges are the edges on the spanning tree. So C2 goes along here, 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 here. That's C2. Now what I'm saying is that C2 is equal to I1, this loop current, plus I4, this loop current. Similarly, if I go ahead, if I take this edge that was removed to form the spanning tree with this orientation, this will form a cycle in the, together with the edges in the spanning tree, it forms a cycle. So it forms a cycle which we call C3. It goes along here, 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 here. So this cycle C3 is equal to I5 plus I2 plus I3 plus I6, because this cycle will enclose all of these regions here. So it's the sum of these loop currents, I1 plus I2 plus I3 plus I6. And then if you look at another edge that we removed when forming the spanning tree, give it this orientation, it forms a cycle in the, together with other edges of the spanning tree. And so it goes up here, 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 and back here. I'm saying that this cycle, which we call C4, is equal to I2 plus I3 plus I3 plus I6, because if you look at it, it encloses these regions which are associated with I2, I3, and I6. And then if we look at this edge that we removed to form this cycle, this edge that we removed to form the spanning tree, it will, with this orientation, it will form a cycle together with edges of the, together with branches of the spanning tree. It will form this cycle here, and this cycle we call C5, and this is equal to I3 plus I6. And then this other edge that we removed, this horizontal edge that we removed to form the spanning tree, with this orientation, it forms a cycle which we call C6. And the C6 here is just the same as the region here associated with I6. So I'm writing C6 equal to I6. Now, when I write these equations, I'm not writing these equations in the same way as I'm writing an equation that equates a number to another number or anything like that. Okay, I'm just using this as a notation to say that this a current in this cycle C1 is equivalent to a current in this cycle, to this loop current I1. And when I write this, C2 equal to I1 plus I4, C2 equal to I1 plus I4, I'm saying that a current in this cycle C2 can be expressed as a sum of these loop currents, I1 plus I4, I1 together with I4. What I'm saying is that if I have, let's say, a flow of x units around this cycle C2, it's the same as a flow of x units around this loop and also x units around this loop. Why is that? Because if I have x units circulating around this loop here, there'll be x units going in this direction from right to left. And if I have x units going around this loop, there will be also x units flowing in the reverse direction along from this vertex to this vertex. So for I1 I have x units flowing this way, and for I4 I have x units flowing in the other direction, and these will cancel each other. So when I add an x units for I1 and x units for I4, I'll get x units flowing around this cycle, which is the same as C2. So that's the meaning behind these equations. It's not algebraic equality or equality of numbers or anything. It just means that a cycle C4 can be expressed as these loop currents, in terms of these loop currents. So we know that any set of currents in an electrical circuit satisfying Kirchhoff's laws can be expressed in terms of C1, C2, C3, C4, C5, C6, in terms of the cycles associated with a spanning tree. And what I've done here is to show that the currents in these cycles can be expressed in terms of loop currents. So from that we can deduce that any set of currents any set of currents satisfying Kirchhoff's laws can be expressed in terms of the loop currents, in terms of these loop currents. So these loop currents are sufficient to express any set of currents in an electrical circuit, in this electrical circuit, satisfying Kirchhoff's laws. Again, I want to just illustrate what I described on the last slide. Let's go back to this. Let's go back to our spanning tree here, and we added this edge which we removed to form the spanning tree, We added this edge with this direction, and it formed a cycle here. That was our C4. The cycle formed from the spanning tree. And we said that that was equal to I2 plus I3 plus I5 plus plus I6. Okay, I2 plus I3 plus I6. That C4 was equal to I3 plus I4 plus I6. If you look at I2, I2 circulates around these green edges here. I3 circulates around these green edges here. I6 circulates around these green edges here. Now, if I have equal values for I2, I3, I6, what will happen is, suppose I have X units for I2, I3, and I6. If you look at what happens along this edge here, you have the X flowing in this direction and the X flowing in the opposite direction, so those will cancel each other. If you look at this branch here, you have X flowing in this direction and you have X flowing in that direction, so these will cancel each other. So overall what you'll have is nothing here, but you'll have an X flowing around the perimeter here, which is equal to X flowing around C4. So this cycle C4, any X flowing around that cycle can be expressed as X units flowing around I2, I3, and I6. So that's the meaning that I've given to the equations that I wrote on the previous slide. So I hope this illustrates how any current that can be expressed in terms of these cycles from the spanning tree can be expressed in terms of the loop currents. Here is example 6. This is a worked example on the method of loop currents. Here we have an electrical circuit, and you have these 9 nodes and these branches. Here I'm giving each branch consists of a resistor. I have 2 ohms on this branch, 2 ohms on this branch, 2 ohms on this branch. All the other branches are resistors of value 1 ohm. Now to this circuit I force currents in and out. So I force 1 amp into this node and I take out 1 amp from this node. I force 2 amps into this node and I take out 2 amps from this node. So I find some way of forcing these currents into those nodes or out of those nodes. I want to find the currents in all of the branches of this circuit. So I'll show you how to do that using the loop currents. So let's continue with example 6. We will look at the forced currents. Remember, these are the currents that we apply. So we are forcing these currents through the network. And we want to find a way of these currents going through the network that satisfies Kirchhoff's laws. I know there's no unique solution to this because there are cycles here. There's no unique way of doing it. So I will just find a way of allowing these currents through the network that satisfies Kirchhoff's laws. So I'm going to use paths here. So this 1 amp, I'm going to pair it with this 1 amp out here. So I'm just using a path. I can use any path that I want here, but I'll just pick this path. I'll go here, I'll take this 1 amp and carry it along this branch, along this branch, along this branch, along this branch, and out. And this 2 amps, I'm going to let it flow along this branch, and then this branch, and then out. So that will satisfy Kirchhoff's laws. If I follow these paths, I get flows that satisfy Kirchhoff's laws. So those are force currents, and I found a way to send those through the network. Now let's look at our loop currents. From the diagram, you can see that there are 4 regions, and with each region I associate a loop current. So it's I1 here, I2 is our loop current here, I3 here, and I4 here. And I give some orientation to the branches, which is shown by the direction of the arrows. And you can express the current in each branch in terms of the loop currents. Okay, I have I1 and I1 following this direction, I2 here following the direction of the loop here, I3 here following this direction, I4 following this direction. Given this orientation, it will be plus I1 and then minus I2. The I2 will go in the opposite direction. Given this orientation, it will be plus I4 and minus I1. Here it will be plus I3 minus I4, and so on. Okay, and on this branch, I2 minus I3. So I've expressed the current in each branch in terms of the loop currents. Now what I will do, continuing with example 6, what I will do is superpose the previous 2 slides. The currents that I sent through the network plus the currents from the loop currents. Okay, so notice here it's the same as the loop currents I had before, but here, remember, there was an input of 1 here and an output of 1, so I had 1 coming down here, so it would add 1 and add 1 and then add 1 here, add 1 here, and then I had a current of 2 going from this node to this node, so it would add 2 here and subtract 2 here. So I've superposed those 2 sets of currents, the force currents and the loop currents. Now we will apply Kirchhoff's voltage law to each loop. Kirchhoff's voltage law says that the current drop around any cycle is equal to 0. The sum of the current drops around any cycle is equal to 0. So let's look at let's look at this cycle here. Here we go around the loops. Right? When we are working with loop currents, the cycles we use for Kirchhoff's second law are just the loops. Okay, so we'll look at the loop with I1. So remember the resistors all along here will be 1 ohm, so it's 1 times I1 plus 1 times I2 following the direction of the arrow, and then we are going against the arrow here, minus 1 times I4 minus I1, that's minus this, and then we are going in the direction of the arrow, so it will be plus 1 times I1. Okay, you have 1 as the resistance in each of the branches here. And then we'll go to the loop represented by I2 and look at the fall of voltages around this loop. Remember, the resistance here and the resistance here will be 2. The resistance here and the resistance here will be 1. So let's look at the drop here. Will be twice I2 and then plus 1 times I2 plus I1, because you have resistance 1 here, and then twice this current here, I2 minus I3 minus 2, and then we are going against the current, so it's minus 1 times I1 minus I2. 1 is the resistance along this branch. So that's our second equation. And then for this loop, again, we will look at the voltage drops along around this cycle. Remember, the resistance here is 2, resistance here is 2. So this gives us, okay, I'm going along this branch first. So it's minus 2 times the current here, I2 minus I3 minus 2, and then plus 1 times the current here. That's the resistance times the current, and then plus 2 times I3 plus I1, and then plus 1 times I3 minus I4 plus 2. And then let's go to this loop here. All of the resistances are 1 in this loop. So let's start here and we go across here. The fall of current will be 1 times I4 minus I1. We are going against the direction here, so the fall here will be minus I3 minus I4 plus 2. In the direction of the current here, of the arrow here, so it's plus 1 times I4 plus 1, and then in the direction of the arrow it's plus 1 times I4. Okay, so we have these 4 equations from Kirchhoff's voltage law. We apply Kirchhoff's voltage law to each loop. So here we rewrite the equations these are the 4 equations. I've just copied and pasted from the last slide, and then I will simplify the equations into this form. 4I1 minus I2 minus I4 equals 0. That's from the first line here when you gather similar terms, and then from the second equation you get this when you simplify. From the third equation you get this when you simplify, and from the fourth equation this is what you get when you simplify. So I have 4 variables here, I1, I2, I3, I4, and 4 equations I can solve to get values. And when you solve, you get these. I've not written it in decimal form, I've left it in fractional form. You get these values for I1, I2, I3, I4. Before we go ahead, let's look at this form for the equations here. Notice the symmetry in this. You have, if you look at the matrix of these coefficients here, you'll have positive numbers on the diagonals, 4, 6, 6, 4, and then the off diagonals are symmetric about the main diagonal, okay, and they have minus signs. It's interesting to notice that. You'll probably learn about that in more detail if you do courses in electrical circuit theory. Anyway, the solution of the system gives you these values for I1, I2, I3, I4. All are negative. So this is what you get when you simplify. Solving, we obtain these. And based on that, just go back to the previous slides where I wrote all the currents in terms of I1, I2, I3, I4. Substituting the values for I1, I2, I3, I4, you get the currents in each branch here. So I solved it completely. I have current flowing down here, flowing across. Okay, I've changed everything to a positive sign also. If necessary, when you have a negative result, you just change the direction of the arrow and write it as a positive value. So I have these. You can verify that there is equilibrium at each node here, and the inputs also at these nodes, the inputs equal to the sum of these values, and so on. So this solves the system electrical circuit, and the method I've used is the method of loop currents. If you wanted the potential at each node here, you can also find it. I've obtained this from the previous diagram. I've arbitrarily let the potential at this node be 0, and then using the current along this edge, this branch, together with the resistance, I get this potential. Use the current along this together with the resistance, you get this potential. Use the current here along this and the resistance, you get this potential. And you can work out all of the other potentials. So if you needed that, you could also find it. Okay, again, the method of solution for the currents was the method of loop currents. Now here are some problems for you to work on. I will leave these with you so you can get some practice. Again, many of these problems involving spanning trees can be done with very simple arithmetic. And someone in primary school or secondary school can handle these problems because they just involve basic addition and subtraction. And you just need to select the order of nodes that you're working on and keep going step by step, and you can find the flows in all of the branches. So the problem here is to find the flows in each branch, and you can use the methods we've previously demonstrated. This is another problem, find the flows in each branch. You can work on this also. And problem 3 here, find the flows in all branches of this circuit. So this is a electrical circuit. Now I've given you the flows in some of the branches. Okay, so you may have attached meters to these branches and measure the currents. What you have to do is find the flows in the remaining branches. So you can work on that also and get some practice in this. Again, it's not very difficult, very simple arithmetic. Thanks again for your kind attention to my video lecture, and once again I wish to acknowledge the support of the University of the West Indies St. Augustine campus in Trinidad. This video goes into detail on electrical circuits and particularly focuses on loop currents, which is the basis for the method of loop currents in solving electrical circuits. And I invite you to view my other video on Trusses, electrical circuits, and Kirchhoff's laws, where I make a parallel between the method of loop currents and a new method, the method of Trusses, which is used to solve problems in indeterminate trusses. So thanks again for your attention, and I hope you keep following my videos.